Welcome, everybody, to this Europlanet webinar on in-situ resource utilization. This one is quite exciting, and we've been planning it for some time. We are going to be speaking today about space resources and in-situ resource utilization. We have two wonderful speakers for you today, Harries and Lauri Siltala, to talk about this very new and interesting topic. We planned this webinar for this month specifically because in 2 months' time, there'll be the annual Space Resources Week in Luxembourg, which is co-organized by the European Space Resources Innovation Centre, where one of our speakers works. So without further ado, I think, Lauri, you are going to start us off.
Correct. I'll just share my screen. And hello, I'm Lauri. I'm the planetary scientist at Karman Plus, which is an asteroid mining startup. It's a very engineering heavy company, so it's besides me, it's all engineers more or less. But yeah, I'll be talking about asteroid mining in general for a few slides and then move on to discussing Karman Plus and our first space mission to an asteroid, which is already funded and should be happening in the coming years. So first, asteroid mining. What is it about? It shouldn't be a surprise to any of you that in general, when you talk about asteroid or space mining in general, the idea is just going to some celestial body like an asteroid or the moon, like in the next talk, I think, and getting some kind of material from there. Callum said in his introduction that it's a very new thing, but actually I feel like people have been talking about this for decades, so I would argue against him here. But either way, it has yet to really materialize, though people have been talking about this for a long time. So the question is why? And in my opinion, these past attempts like planetary resources and deep space industries were a bit too early. The economics, the launch costs were not yet quite there. And also they have then tended to lack focus, kind of using their limited resources on getting sidetracked instead of focusing on the core objective. That's my opinion. But the current situation is that space is getting more and more commercialized, for better or worse, and the launch costs are going down, and spacecraft are becoming cheaper. So as we see it, potential customers are starting to appear, and the economics are becoming more viable. And so we at Karman Plus think now is the time to make this happen. So one common question is why go to asteroids rather than the moon, which I will be talking about in the next presentation. Our opinion is that some near-Earth asteroids are easier to reach than the moon in terms of delta V, and they are also easier to leave because there's no gravity, well, unlike with the moon. Of course, lunar mining does make more sense if you want to do projects on the moon itself, but we think otherwise asteroids are the better approach. Third, because we have plenty of scientists here, a relevant question is why should you care about this as a scientist? Well, if asteroid mining becomes commercially successful, that will lead to a massive increase in space missions to near-Earth asteroids, and by extension, you'll be getting a lot more data for your science to do research with, which I'm sure will be exciting for plenty of scientists. Also, when you look at, for example, the oil boom of the 18th century, which is, well, environmental issues and such aside, that led to massive funding increases in, for example, geology and geophysics. And a lot of modern science is kind of founded on the oil in that sense. And I'm expecting that an asteroid boom could do the same for planetary science. So if this becomes a big thing, you guys can hopefully get a lot more funding. Next question is, what exactly do we want to mine from asteroids? General statement I want to make at first is that because it costs a lot of money to launch stuff from Earth into space, it follows that anything in space is worth more than it is on Earth. So, for example, if you look at water, it's cheap on Earth, but it's not cheap in space, and you can theoretically make money from selling water in space. But on the other hand, the market in space is much smaller than Earth. So from this, it follows that it looks like there's two separate approaches to go for with asteroid mining. One option is that you go to mine something expensive on Earth, like people talk about platinum group metals a lot, and then send the materials from the asteroids to Earth itself. Like our competitors, Astroforge, are, for example, aiming for this approach. And with this, the market already exists. Like you have plenty of people on Earth who want these platinum group metals, so that's a big plus. but you get additional challenges from things like figuring out atmospheric re-entry, which is not trivial, but of course it's possible. We've done this before with OSIRIS-REx and Hayabusa 1 and 2. And third, people in the media often hype these metallic or M-type asteroids as very exciting targets because of these metals for asteroid mining. But actually, in my opinion, it's not really certain what these asteroids are really like, and it's not clear if they will live up to the hype, because we have never visited a metallic asteroid, though maybe the Psyche mission should change that very soon. So the other option here is to mine and process regolith for materials to be used in Earth orbit instead of on Earth itself, and we at Karman Plus are kind of aiming for this approach. Here, people most often talk about water because you can, for example, make rocket fuel from it. But there's also promise in, for example, using phyllosilicates or clays, which are plentiful on carbonaceous asteroids, as manufacturing feedstock, like space ceramics and such, which are possible in theory. Here, there's not much of a market yet, which is kind of a weakness, but there is for sure growing significant commercial interest in servicing or refueling satellites to keep them alive for longer, because satellites are expensive. So I am expecting that the market will form here as well in the coming years. Next, some of the example challenges we have to face in asteroid mining. First of all, space is getting cheaper, but it's not cheap, of course, and there are questions about whether this can actually get profitable. Our thinking is yes, but we'll have to prove it and see. Next, we have found that the existing infrastructure for deep space communications is actually very important, but also very limited. It's not easy to find good communications and that's at least in part because there are no commercial deep space missions at the moment. So I'm hoping that will change in the future. On the observing side, we have plenty of easily accessible near-Earth asteroids that are known, but it turns out that the overwhelming majority of them have no physical characterization at all. So if we go to one of those, it's kind of flying blindly. Of course, the situation there is improving every day as new surveys come online and existing ones take more data. Then we have challenges like figuring out the best approach for actually doing this asteroid excavation at scale, and questions like refining the material on the asteroid itself. How do we do this? And maybe we can make our own return fuel when we bring stuff back. People have been thinking about all these things. We are as well, but no one has yet done these things in practice, so we'll have to figure out the best way. Next, a bit about Karman Plus. So we at Karman Plus are an asteroid mining startup based in Colorado in the US. I was the first hire after the founders, actually, so I've been here for a while, but I myself work remotely from Finland full time. Our mission is, to quote, to use space resources mined from near-Earth asteroids to provide abundant, sustainable energy and resources in space and for Earth. And as I alluded to before, we are particularly interested in water and phyllosilicates for rocket fuel and manufacturing feedstock in space. What I like and what I think you guys also will like is that I see us as a science-friendly company with open values. The intent is absolutely to publish our spacecraft data about the asteroids we go to for scientists to use for science as well. We're not a science company, but we value science very much. And finally, our primary success indicator, what we are trying to optimize for, is the cost per kilogram of regolith that we deliver, because for this to commercially make sense, we have to be able to supply material for cheaper than it would cost to send the equivalent material up to space from Earth. So next, a bit about our first mission. We are working on a near-Earth asteroid mission called High Frontier. It's fully funded, which is always nice, and it's going to be happening for sure. And overall, we're going to be launching in the first quarter of 27 and probably finish the mission in 28. And we're going in with a budget of less than $20 million, which is kind of nothing when you compare it to commercial or science agency missions and such. Overall, what we're going to do is we're going to some near-Earth asteroid, capturing a sample at a scale of multiple kilograms, and transmitting data to Earth to confirm that we successfully captured this sample. So it's kind of a tech demo mission at this point that will prove our capabilities and also kind of be a learning experience for us. We're not actually bringing the sample back with the first mission, but in the future we will for sure. We also have some extended objectives about multiple tag attempts to test various excavation methods and autonomous operations and so forth, and also some science. Next, a general overview of the concept of operations and the timeline for High Frontier. So we are going to be doing a ride-share launch to sun-synchronous orbit in the first quarter of 27, as mentioned. We have a launch booked on SpaceX Transporter 19. Then the question is, how do we actually get to an asteroid from SSO, because it's not a deep space orbit or anything? What we're going to be doing is a spiral out maneuver to escape Earth. It will take about 6 months or so, and this, as we see, it minimizes our launch cost, but it comes at a time and complexity, and also will, I think, take the majority of the delta V of our spacecraft itself. This will be followed by an interplanetary cruise to our target, which is, of course, depends on the target, but it's probably more than half a year, and we'll be doing this with autonomous optical navigation. We have to do this with as much autonomy in general as possible to reduce communication costs. And finally, when we get to target, we'll be doing proximity operations for about 2 months. We'll be mapping the target asteroid with autonomous algorithms and taking higher resolution images of interesting areas, selecting landing sites, and then doing the tag attempts. And after that, the mission will be concluded, and overall, the maximum duration we're going for is 15 months. So we should be finished by mid-28 at the latest or so. Next, a bit about the hardware. We're going to be building the spacecraft ourselves at Colorado, and as a rough idea of the size, we'll be talking about the 250 kilogram dry mass or so. We'll be going with electric propulsion with plenty of delta V, like aiming for 14 kilometers per second when I last heard, which is actually going to be the record for the highest delta V electric propulsion spacecraft ever. On the payload side, we're going to have 2 excavators developed in-house. I have CAD models here with the top right one kind of being a gripper with these cool micro spines along the arms that works very well for gripping to various objects. So it's kind of made for plucking boulders of asteroid surfaces. And on our testing so far, it works very well. But I personally am a bit concerned that boulders might break up if we pick them up, because some asteroid boulders might be surprisingly weak, but we'll find out and see. The other one, the bottom right, is it's more like a kind of a mouth we push into the asteroid, made for softer regolith or such. It will clamp shut and then pull back, and because there's no gravity, the regolith will be delivered into our sample container, so that can be used multiple times easily. We'll be having a third-party science payload as well. I'll talk about that in a bit, and camera systems, which I will also talk about in a bit. Before the payload stuff, let's talk about our target profile a bit. How do we select our target and what it might be? Well, most obviously, the first criterion for a possible target is reachability. We have to be able to get to our asteroid, whatever it is. And we have an internal, what we call a leaderboard, which takes all the known near-Earth asteroids, filters out the list to what we can actually reach with our desired mission parameters, and it will compile together what we know about them in the literature. And finally, we get a list of candidate asteroids. There's an example plot from our leaderboard kind of showing a list of reachable asteroids with some spacecraft configuration, when we need to launch at the latest to get to them, and when we would arrive at them. But a bit about our preferred targets. After this initial filtering, it quickly turns out that nearly every target on our list is completely uncharacterized physically, but fortunately, not all of them are. In a physical sense, as we see, the rotation period is the key parameter, because High Frontier is fairly agnostic as to the composition of the asteroid, but we assume that fast rotators can be depleted in loose surface material because of the centrifugal force, and we rely on the existence of this material. So that makes the rotation period the key criterion for us. All this filtering leaves 2022 DC5 as our primary target because we know it's a slow rotator. The composition, on the other hand, is a bit unclear. We have photometry saying it's an X, S, or C type, so these are very contradictory. But we have some preliminary thermal modeling, which is most in line with a C type as well, so I'm inclined to believe that. We also have a backup target in 2022 UH2, which is also a fairly slow rotator, but the composition is completely unknown. And I note that both are observable in early 26, so if you are interested and have time to observe, please feel free to get in touch. I'm also looking at that on my end. Next, a bit about the science payload. We had a couple of years ago an open call for proposals for science payloads from third parties to include on High Frontier. We ended up accepting one proposal from the University of Tokyo. They have JAXA support for this as well. And it's called the Surface Dielectric Analyzer. It's based on an instrument that's going on Artemis 3 as well. And what it's going to do is measure the dielectric permittivity of the asteroid surface. They're also talking about including some additional instrumentation like Vivaldi antennas and a neutron counter for volatile detection, but those are not officially selected. I'm not sure if they will fly, so no promises there, but there are other options as well. And we have, of course, finally, as about the camera systems, because you're scientists, you might be excited about this one. We are going to be planning to map the entire target asteroid. We have to do this for selecting the landing sites, and we'll be doing global mapping with a 10 centimeter resolution. There's a simulated image in the top left there, followed by high resolution images of particularly interesting sites with a 1 centimeter resolution, with, again, simulated images to the top right. The unfortunate thing is that we won't be downlinking these back to Earth at full size, but we'll be downsampling them heavily, though because of communication limitations, but we'll be sending some individual interesting images at full size for sure. Separately, we have cameras for observing the excavators, including actual videos of the excavation process itself. You'll see, again, simulated images there on the bottom with both our excavators visible as well. So we'll be seeing how they work in real time. Whether it's monochrome or color is kind of remains to be seen. The cameras themselves are monochrome, but we have talks about including some kind of filter wheel right now for some rough physical characterization. And I'm going to conclude here by saying that I think the coming years are going to be very interesting to asteroid mining enthusiasts, because both us and Astroforge are launching fully funded space missions to near asteroids, which is kind of a stage no past asteroid mining company has actually ever gotten to. So it's getting more concrete now in the coming years. And I'm hoping that we'll get you scientists some new exciting data to study from these missions as well. And hopefully, if this goes well, we'll make asteroid mining a real thing, and we're definitely going to try our best. So I'm going to conclude here, and thank you.
Thanks, Lauri. Reminder for all of our attendees, please post your questions in the Q&A tab at the bottom of your screen. We'll get to them at a Q&A session after our second talk. It's from Dennis Harries from ESRIC. I'll hand over to you, Dennis.
Thanks a lot. So I'm going to share. Yeah, welcome. Lauri gave a really nice introduction and some really important aspects already. I'm working at ESRIC, which is the European Space Resources Innovation Center. So we are a public institute. I will tell about a little bit how this came to happen. I'm actually an asteroid scientist by training, but I turned a lunar scientist because our focus on ISRU is using lunar resources. And many people have the first question, why do we do this? And at the end, it is the desire to explore. So our mission is to strengthen and coordinate activities to help explore space, to enable humanity to go into space in a sustainable manner. So we are not the ones who want to get rich, but we want to advance what we can do in space. And I've looked up two quite famous references from two public figures in the field of space resources. One is Angel Abud-Madrid, who coined the term living off the land. So one idea of using space resources on the lunar surface is to support the human presence on the lunar surface, like a long-term and sustainable human base on the lunar surface. And Clive Neal put it in a bit different way. He said science enables exploration and exploration enables science. And this is also what Lauri emphasized. So whatever we do in space, may it be commercially or may it be just out of curiosity, out of the drive for exploration, will in the end benefit science. So this is, I think, a great plus from this concept of ISRU. It will in the end benefit science and help us to better understand the places we are going to, because this is something we have to actually make this whole concept of resource utilization work. A little bit about ESRIC. So ESRIC was founded in 2020 as part of the Luxembourgish spaceresources.lu initiative. Its creators are the Luxembourg Space Agency, which is part of the Luxembourgish Ministry of the Economy, and the Luxembourg Institute of Science and Technology, which is hosting us physically here in Luxembourg. And just right after its creation, ESA became a strategic partner. So we are not an ESA center, but we are in a strategic partnership with ESA. And I will show some example how this works. Right now, today, we have 25 people working here at ESRIC, about 45% are females. We have 6 PhD candidates, so we are actively working on research, and we have around 20 projects or activities currently going on. And about 50% of these projects are in partnership with ESA. And why Luxembourg? So Luxembourg did have a long history of space. So it's we have the headquarters here of SES, a important satellite comms company. And Luxembourg at the same time had a long history of mining and iron and steel processing. So this taken together led the Luxembourgish government to decide to venture into this area of space resources. And we are based in Belval. You see this beautiful image of the blast furnaces, which has transformed from an industrial area to a science city in the last 10 years or so. And we are far down in the south of Luxembourg. And this offers me the opportunity to remind you there is a Benelux hub in the Europlanet Society. So I'm the representative of Luxembourg. We are not so many people currently in planetary science in Luxembourg. So if you're interested and if you are a member of the Europlanet Society, you are welcome also to join the Benelux hub and maybe engage with us a little bit more. But a little bit more about the research we do. So initially, as I said, I started as an asteroid scientist. So I worked with samples from the Hayabusa missions. Now I turned a bit more lunar geologist. So all we do is sort of focused on the lunar regolith. So you see this iconic picture of Buzz Aldrin's footstep on the lunar surface. So this is the material we are aiming to work with, and more or less everything is sort of connected to this powdery regolith. And I like to just give a few spotlights on a few projects that we are doing. This is an overview of our work. It starts with what we call prospection, so understanding resources, doing remote sensing, analyzing remote data, trying to geologically understand how certain resources formed, how these led then to what we call deposits. And we think of how we then can utilize these deposits and resources. A main focus is the production of oxygen. So we had this famous quote of living off the land. If we want to stay on the surface, have a sustainable lunar presence on the lunar surface, we need to produce oxygen and water to provide the basic requirements for human life. And we're exploring various technologies to extract the oxygen that is plentiful in this regolith, but very tightly chemically bound in the minerals. And I will give some examples of this. We look into other ways of regolith processing. We use microwaves to sinter and melt regolith, because another important requirement is you have to have some solid surface for landing your spacecraft. So landing pads are an important aspect of actually being present on the lunar surface on a larger scale. So we need to learn how to turn this powdery regolith back into some sort of solid form. We look into beneficiation. That means we take not the regolith as it is, but we want to separate the regolith into certain components that we can process and that make sense for our downstream chemical processing. And at the other end, then we have to purify the extracted water and the oxygen that we get out of the lunar materials. One important aspect is that we want to be sustainable. So we look into recycling materials. So circularity is an important aspect of working on the lunar surface. And this is also an important export back to terrestrial economy. So we try to optimize systems and processes in a way that they are more circular. So we try to analyze what are the waste streams that can be avoided and that can be utilized in a most effective way. We have laboratory infrastructure. So this is part of my daily work to keep these laboratories running. These are facilities that are partially funded by ESA. So some of the demonstrators that we have in the lab and that we will receive in the future are funded by ESA. So we have a processing lab. Then we have an oxygen extraction lab with one of the first demonstrators from ESA already running. And we have a purification lab. In the future, we will receive a dusty thermal vacuum chamber that will have 2.2 meters diameter, which can simulate the lunar surface environment in terms of pressure and temperature, which will then also be available through ESA to the community to test various systems and subsystems under realistic conditions. And right now we're also engaged in the design study into scaling up the electrolytical production of oxygen from lunar regolith, the ground-based pilot plant, and I will talk a little bit about the chemical process behind this in another slide. But before I do this, I would like to go back to this very important aspect of doing prospection. So as Lauri mentioned, it is important to explore the localities that you're going to. So mapping and reconnaissance is a very crucial first step. An important trope that we are often facing is the famous resource to reserve problem. So we know we have resources on the moon. We have samples from Apollo, and the same applies to asteroids. We have samples from Hayabusa. So we know there is material that is interesting for utilization. However, the question is how much is there, and is it available or reachable in a way that it makes economically sense? So is there a recoverability that somehow aligns with either budget or economic constraints if you're a private company? So this requires remote sensing, and this example is from a recent paper from my fellow planetary scientist colleague Abigail Casada-Diaz at ESRIC. It looks at the basic workflow, how you have to go from just the basic understanding from remote sensing towards a quantitative understanding of how much material is available in the deposit. This example is for the mineral ilmenite, which is an iron titanium oxide, which is very interesting because it is relatively easy to reduce. So you can remove the oxygen to produce breathable oxygen in the end, or oxidant for your propellants. And it is also quite interesting for the mining of helium-3. So some people are interested in mining helium-3, and ilmenite is one of the mineral with the highest retention of implanted solar gases. So if you would want to mine helium-3, which occurs in tiny concentrations on the lunar surface, you definitely want to look for the ilmenite, and you want to go to a place where you have both the maximum concentrations of ilmenite and helium-3, and that requires a lot of modeling work, spatial models, and a very good geological understanding of how these deposits evolved. So this is a very important aspect before we even start about thinking of technologies, how to extract certain elements. Right now, we are not venturing into the field of extracting helium. So our focus is, as I said, the extraction of oxygen. And the very first demonstrator system that we have here at ESRIC is the Alchemist. So this is an ESA procured system that takes this ilmenite, this iron titanium oxide, reacts it with hydrogen to make metallic iron, titanium oxide, and water. So ideally, you would split that water into hydrogen and oxygen. You would use the oxygen in your downstream application, and you would send the hydrogen back into the system to reduce more ilmenite. This has been tested so far. We've now spent almost 3 years setting this up because we're working with a large amount of hydrogen here in the system. So we have very tight safety constraints, but we are now at the point that this is again running, and we will soon start setting up our experimental routines. And the other currently much favored way of extracting oxygen is the so-called molten salt electrolysis. Also, here we will receive ESA demonstrators later this spring, and this process is based on the so-called Frey-Farthing-Chen Cambridge process, or FFC Cambridge process, that uses molten calcium chloride plus electricity to split these metal oxides that you have in the regolith into the metals and oxygen. And the nice thing about this process is that you can almost extract all the oxygen out of your regolith. With the ilmenite, you can only do this process with maybe a few volume percent of the ilmenite that is in the regolith. With the FFC process, you can almost extract all the oxygen that is in the material. It comes with a drawback that this molten calcium chloride is an extremely corrosive material. You have to work at high temperatures with a lot of oxygen around. So this poses really big challenges in terms of material compatibility and stability. But this is something that we will test with systems that we will receive from ESA. The nice byproduct is metal. So this process will not only produce oxygen, it will also produce metals that then can be used for other purposes, such as doing metal 3D printing and producing various parts for our lunar habitat. A third possibility of getting hold of oxygen and especially of hydrogen that you also need is to use the lunar volatiles. So we know the south polar regions of the moon have permanently shadowed craters. These craters are extremely cold, and we expect that these craters host water ice, but also other volatiles such as ammonia and hydrogen sulfide. There has been so far one data point produced by a NASA mission called LCROSS, and this actually impacting spacecraft has shown us that there are volatiles in these permanently shadowed regions. We still don't know how much there is and how variable these volatiles are in these regions. We expect a very high level of heterogeneity because the temperatures vary largely both in space and time across these regions. But they contain several very, very interesting elements. This includes nitrogen in the ammonia and carbon in probably carbon dioxide or even in hydrocarbons. So nitrogen and carbon are two elements beside the hydrogen that are extremely limited on the lunar surface. So if we want to establish a permanent presence on the lunar surface, we are required to somehow source carbon, nitrogen, and hydrogen. And that's where Lauri comes back in with the asteroid mining. These elements are fairly abundant on asteroids. They are very scarce on the lunar surface. And in the future, that would be probably a good combination to supply the lunar surface with carbon and nitrogen from asteroids, and maybe locally mine the oxygen on the moon, or the hydrogen, which also may be supplied from asteroids. One problem with this is that some of these components that you will get out of the extraction are very, very toxic. So ammonia and hydrogen sulfide are surely not the molecules you want to have in your air, in your habitat. So what we are currently studying together with the company Air Liquide and ESA is how we can purify these gases. So we're looking at adsorption technologies to remove and at the same time separately recover these compounds, both to produce clean water and oxygen, and on the other side to recover these compounds selectively to make use of these geochemically very limited elements on the lunar surface. And this is how it looks in the lab currently. So this is also part of our daily work to make a good understanding of this mess we are doing in the lab with hundreds of cables running around. At the end, I want to give you a little bit outlook on how we think the future of implementing space resource activities will look like. So what we are focusing is on the research, on the laboratory proof of concept. The next few years will certainly see demo and science mission, something that Karman Plus, for example, is doing with asteroids. We will see this in a similar way for the lunar surface. It has been started with the NASA CLIPS missions, and that will continue with more both private and public missions. Later we will see pilot scale missions where we'll actually plan some sort of pilot demonstrator on the lunar surface to scale up and understand better the requirements for scaling up these technologies, which then at some point will lead to sustained and scaled operations on the lunar surface. Part of our mission is to enhance the involvement of private companies in this development. So ESRIC is having a startup support program where we incubate early startup companies that want to take up this challenge to operate in space And we are also right now in the process of establishing a accelerator together with ESA to also support more established companies, for example, with the lab equipment that we have. As Karman mentioned, there is the Space Resources Week every year. So this year it's the 19th to the 21st of May here in Luxembourg, so where the community meets. And we're also hosting, or this year we are organizing together with ESA, the ESA ESRIC Space Resources Challenge, which is an event that will take place then in the new lunar facility at ESA DLR in Cologne, Germany. The call has closed, but this is focused on a challenge where we invite teams from industry and academia to compete on a certain topic. 2021, it was the challenge of prospecting lunar resources. In 2024 and 2025, it will be to excavate, robotically excavate resources and separate certain components from these resources. And this will be some part of a quite exciting demonstration later in October this year in the lunar facility. And you can also find this on our ESRIC website and on the ESA website to follow this. And there will be more challenges. So this challenge-driven innovation is a now established theme in the space resources community where various teams compete for a certain prize. So in this case, it will be a development contract with ESA of €500,000 plus potentially 250,000 euros from the Luxembourg Space Agency to further develop critical technologies for ISRU. And that's from my side. Thanks a lot.
Thank you, Dennis. Okay, we have a little bit of time now for some questions. We have about 10 minutes left if we need them. So if you have any burning questions that you haven't been posted in the chat yet, then please do so now. We have two questions so far. The first is from Didier, who says, you are, if I remember well, a joint venture with US companies. What is the effect of the actual policy in the USA for space impacting your objectives?
Yeah, I'm assuming this is for Dennis, given the timestamp.
Yes, I expect so. Nigel says he had the same question as Didier.
Well, we are not really a joint venture with US companies, so we do work a lot with ESA, and NASA. And right now we don't yet see the consequences of the recent political developments. But from what is discussed as very thorough cuts to NASA, it is expected that, of course, this will have consequences also for us working with our partners at NASA. The transatlantic cooperation has never been that easy because other than in the science field, the economic aspects of space resources makes it a bit more difficult to work with NASA across the Atlantic. So, and this is probably not going to get easier.
Thank you. Yeah, these recent developments are affecting all corners of the sector at the moment. They seem to be a very hotly debated topic. So thank you for weighing in. We have a question from somebody who'd like to remain anonymous. My question is to Dennis. You mentioned about making and installing a chamber that will have ultra vacuum and extreme temperatures to replicate lunar environments. Are you also considering any interface of radiation? If yes, which ones and at what energy?
So right now, the chamber, the DTVC, is designed for testing hardware under the influence of dust. So this is the main objective. It has been designed in a way that it could be in the future equipped with a solar simulator, but this will not be available in 26 when it's going to be commissioned. Beyond that, we do not foresee currently testing radiation, be it ionizing radiation or electromagnetic radiation. But the planning has been clearly to make this sort of modular, so to be able to extend this with various experimental modules, and the extension to radiation testing might be clearly also an option for the future.
Thank you. We have a question for Lauri from Pablo, who asks, what are the possible collaborations between Karman Plus and the scientific community right now? Any specific examples?
Yeah, so there's plenty of different areas here. Like for starters, I mentioned we have an external science payload by third-party scientists on our spacecraft itself. So that's an example of a concrete collaboration. But otherwise, we have things like, I also mentioned that in my presentation that we have preliminary thermal modeling for our favorite asteroid 2022 DC5. And that came to being because I noticed there is some unanalyzed NEOWISE data for this asteroid and set up a collaboration with a thermal modeling external planetary scientists as well. So we have been collaborating in thermal modeling as well. And then we're looking at, for example, observing, for example, Peter Pravec's group has observed light curves of possible target asteroids for us at my request. I know Manos has also observed targets at my request. And we're looking at observing proposals for these top targets with some external scientists as well in the near future. So those are some examples, practical examples that we have been doing.
Thank you. Mansi asks, exciting to see the developments. Are there opportunities to get involved with in-situ utilization for early career scientists? I suppose this could be answered by either or both of you.
Yes, maybe I can start. So, of course, the Space Resources Week, another shameless plug, is a really good start. And this year, on the day after the Space Resources Week, there will be also a early career event here in Luxembourg at our facilities down here in the south of Luxembourg. And I think you find the details on the Space Resources Week website, or they will be posted there shortly. And of course, we are hiring. We are still growing. So we have on a yearly basis, maybe 2 or 3 positions for postdocs. And we also have PhDs, PhD candidates in our team. So we are actively also engaging in developing the workforce for space resources in Europe and Luxembourg.
Thank you. Didier has sent a follow-up. Didier was our first question about what the effects of US policy on our objectives here. He says, thank you both for these nice talks. Are you fully involved in the Lunar Village project of ESA? Are you also considering the Mars exploration in your strategic plan?
Yes, so we are involved with the Lunar Village Association. So we had a very successful meeting last year in December here in Luxembourg with a lot of international attendance. The question is, or the way I understand the question is, how do we see the progression from going from the moon to Mars? So it was always proposed that the moon will be an important stepping stone for going to Mars. So I still think it is important to set up a sustained human presence on the moon to learn very, very critical skills and develop technologies to actually go to Mars. I doubt that it will be successful if you try to go to Mars directly from Earth just by bringing a very large spaceship there. I think we really need the time and the lessons learned from doing lunar ISRU to actually better understand how to transfer this to Mars.
Thank you. Nigel commented in the chat a suggestion to use the Europlanet telescope network for observations. I've just put a link in the chat for those who aren't aware of it. The rolling call for applications is currently closed, but if you're not aware of what goes on in the telescope network and what has been going on in the past sort of 4 or 5 years under the recently closed research infrastructure, then I recommend you to go and check it out.
Yeah, I can comment on that. At Karman Plus, our targets are so dim, even at their brightest, that I think the telescopes that are part of this network are a bit too small to do proper science with.
Okay.
And it's a possibility for the future, but right now, with our top targets, it doesn't seem like the best choice.
Thank you. Okay, I think we've reached the bottom of our questions. So all that remains really is to thank our speakers, Lauri and Dennis. Thank you for taking the time this afternoon to speak with us. Thank you to all of our attendees for coming and joining and interacting in the chat and getting involved with your questions. Thanks again, everybody.